Between March 9th and 15th, 2026, the airspace defense architecture at Barksdale Air Force Base was exposed as critically vulnerable. Over 7 days, swarms of 12 to 15 small unmanned aerial systems penetrated restricted airspace, bypassing defenses to loiter directly above B-52 Stratofortress flight lines. This incursion occurred despite the presence of the multi-billion-dollar USAF NINJA program. NINJA, designed to intercept and decipher commercial radio frequencies to force drones down, was completely blind to these swarms. The adversaries executed a specific evasion taxonomy. They replaced commercial signals with custom, encrypted control links, rendering standard protocol breaking and frequency triangulation useless. More effectively, they operated in total radio silence. Relying entirely on pre-programmed flight paths, inertial navigation systems, and visual odometry, the drones emitted zero electronic footprint. This exposes a flaw in legacy electronic warfare. Traditional defense relies on the assumption that an incoming drone must talk to a human pilot. When the electromagnetic spectrum is ignored, active sweeping arrays have nothing to lock onto, and the threat slips right past. In an era of autonomous flight, where a drone doesn't transmit a signal, the reliable way to detect it is tracking the physical movement of the platform itself. Shifting to physical detection requires high-refresh K-band radars and multispectral optical and infrared cameras. Fusing the data from these sensors generates an enormous telemetry stream. The system has to process tracking vectors, camera gimbal angles, network queue depths, and classification probabilities all at once. Mathematically, this creates a joint probability space known as the d-dimensional tensor P. Because these variables are heavily interconnected, this data structure grows exponentially with every incoming high-fidelity ping. Standard commercial hardware attempts to load this massive tensor directly into physical memory, triggering a mathematical failure known as the curse of dimensionality. The tensor is too large to query instantly. Processing slows, creating a reactive latency bottleneck across the network. In practical terms, this bottleneck introduces a 500 millisecond delay between where the sensor sees the drone and where the system thinks it is. Against a fast-moving quadcopter, that half-second delay creates a 50-foot tracking error. If an interceptor relies on this delayed track, it will fire at a stale coordinate. Upgrading physical sensors is ineffective if the network architecture cannot process the resulting joint probability space in real time. To bypass this memory limit, the Predictive Tensor Control Plane, or PTCP, uses a slow path architecture to compress telemetry at the sensor edge before reaching the operation center. Raw telemetry is first normalized to establish a pattern of life baseline. The system maps these discrete data states using kernel density estimation. This chart illustrates how the KDE smooths the incoming points using an adaptive bandwidth, calculated precisely by this formula. Normalized, PTCP avoids the memory wall, completely bypassing the full tensor in RAM. Instead, Tensor Train approximation decomposes it into small, interconnected 3D cores. This multilinear algebra transforms the complex data into localized, manageable cores. Even broken down, the system must still account for rank inflation, where an excess of variables could overwhelm localized processors. To counter this, the architecture applies singular value decomposition, or SVD, to identify and strip away negligible probability states. By truncating this statistical noise, the system keeps the memory footprint bounded, shedding the data points that don't contribute to an accurate track. With the data compressed, localized ARM processors can evaluate the entire airspace model at the microsecond scale. This pre-computation mathematically resolves the curse of dimensionality, allowing for real-time edge processing without a centralized mainframe. That localized processing enables the PTCP fastpath, where the compressed tensor cores are embedded directly onto the camera and radar hardware. The system instantly evaluates incoming states to flag pathological or anomalous flight behaviors. This formula continuously calculates a logarithmic anomaly score. A high score means the flight path deviates from the pattern of life, triggering an immediate threat flag. This anomaly score entirely bypasses human operators. It directly drives the physical hardware, instantly actuating camera gimbals and radar arrays to track the target. To maintain a perfect lock, the system uses optical flow kinematics to derive the true target velocity from the video feed. Because the camera itself is panning and tilting, the system subtracts that commanded background motion from the apparent motion of the pixels. This equation, the brightness constancy constraint equation, deterministically evaluates those velocity vectors as they arrive. The result is a physical tracking loop that holds an actively evading target dead center in the sensor array. By combining tensor compression with optical flow, the PTCP eliminates the need for radio frequency data. The tracking loop is mathematically closed using the adversary's own movement. This architecture is currently deployed and active at Travis Air Force Base. The system's objective is to translate probability directly into kinetic force. This is the Anduril Anvil, an autonomous quadcopter interceptor designed to physically ram enemy drones out of the sky. Historically, drone interceptors required active communication links to receive continuous targeting updates from ground stations. Under the PTCP network, interceptors are guided internally by untethered physical optical flow data. Because the Tensor Train compression operates at the sensor edge, the system generates tracking updates at the microsecond scale, bypassing the reactive latency of centralized networks. The interceptor strikes its target using physical momentum, guided by data that matches the drone's actual kinematic state. This hardware-level integration provides a solution for a kinetic strike that is independent of the adversary's encryption or navigation modes. By replacing reactive jamming with predictive modeling, defensive networks utilize an adversary's own movement against them. At Travis Air Force Base, the absence of a radio signal is no longer a vulnerability. It is the starting point for a physical interception.